So we're going to start section 2.1. Now, we just got done with a limits unit, and limits are really the basis of calculus. Everything is built off of this idea of the limit, and we're going to kind of see how that's utilized in calculus, because calculus is really broken down into two parts. One is differentiation, the other one is integration. We're today just going to talk about this idea of a rate of change, the average rate of change versus the instantaneous rate of change. And we'll get into the idea of differentiation and integration later, beginning with differentiation. We'll do that for several units, and then we'll get into integration. But I want to talk about something like something that you are all actually familiar with, the average rate of change. So what is the average rate of change on this function on this interval? And I'm gonna, so this interval is from x equal 1 to x equal 5. And I'd love for you to pause and write down what you think the average rate of change is. If you are back now, we can start talking about what that average rate of change is. When we think about the rate of change, the idea behind a rate of change, if we were to kind of say, well, what is even the units of the rate of change in here? So it's a rate, right? So if you think about the rate of change, this idea of rate, and this is maybe some graph that shows time in seconds and height in feet. And maybe it's somebody threw or he had a projectile go up, and this is what happened with the projectile. Maybe it's a fireworks, maybe it's something else. But when you think about the idea behind rate, wouldn't it suggest that the rate in this particular thing would be feet per second? That would be the unit. And if that's true, then when we talk about what that would be, is we're really talking about the idea behind, oh, well, we have a difference in heights over here of 100 or 400 minus 144. That was our change in height, divided by 5 minus 1. Well, if you think about what that is, isn't that just the slope? And specifically, it's the slope of the line that would go in between these 2 points, right? I mean, specifically, that's the slope of that line. That would suggest, if you did that, 400 minus 144 divided by 5 minus 1, I think that works out to be 64 feet per second. That would be the rate. That would be the average rate. However, that would be the average rate that this projectile is going in the first, between the seconds 1 to 5. We can get a time for that. The idea behind this is what we would call, this whole thing in here is called a difference quotient. It's a difference quotient because it's the difference, which means subtraction. It's a quotient because it's division. That idea behind that is the idea of what's called the average rate of change. So when we think about average rate of change, we're just averaging things, and in this case, that's really just the slope. The average rate of change is the same thing as the slope of a secant line. Okay, so know that this red line right here is a secant line. So that's the idea behind the average rate of change. So if you think about it, here's what we have. We're kind of looking at this right here. We got this graph here, kind of goes in and says, okay, well we're gonna take a change in the height. So this remember that thing, that triangle stands for change. So this right here is the change in height divided by the change in time. And if we do that, we get 64, and that's just over that little interval, and that's the average rate of change of this projectile that is being launched, from the ground, and then ends up landing back at the back 10 seconds later, lands back on the ground, goes up to a maximum height of 400 feet, does it in 5 seconds, and then lands back on the ground over there at 10. When we start to talk about the idea of the instantaneous rate of change at 1, so let's think about what would that mean, the instantaneous rate of change at 1. So I'd love for you to just pause this and kind of think to yourself, what does the instantaneous rate of change mean? All right. We could draw this secant line from the 1 to the 5 and those two red dots, and that's the average rate of change. But in order for us to really think about this idea behind the instantaneous rate of change, wouldn't we need to move this point closer this way? Wouldn't we really need to squeeze this gap in here? We'd love to squeeze that gap. If we squeeze that gap, this gap gets smaller. So when you think about the instantaneous rate of change at 1, that really refers to the slope of a this, I'm trying to think of the best way to say it, but really the slope of a line when x equals 1, and I'll show you what I mean by that. So when you're thinking about the instantaneous rate of change, we're really looking at the slope when it equals 1. So in the notes, I have this Desmos calculator that I'm gonna pull up, and it uses this same graph. So let me pull that up right now. So here's this graph, and this is the same thing. It actually is a parabola. The equation of the graph is right up here, negative 16 x minus 10. So the idea here is use the slider to fix the x value of the point you want to find the tangent. So that's what this slider is right here. I stuck it at 144. So I could move this point right here, but that's where I want to leave it. Use a slider to show the secant line becomes a tangent line when we take the limit as h approaches 0. So let me show you what I got here. H right now is 4, and h refers to this difference between these 2 points, 1 and 5. That h value was 4, much in the same way it was back here. That change in t in this case is using h over here on this one, but it's this idea here that I'm taking the slope, and we'll talk about this in a second. But when this point is at 5, notice the slope is 64 right here. Okay, that secant line is slope is 64. But well, notice what happens when I start to drag this thing. Our secant line starts to change, and notice what the slope is doing. Here the slope is almost 78. If I keep on going, I'm moving the slope further and closer and closer to this other point. I'm kind of squeezing these points together. Now I'm up to 99. I move this thing closer and closer. It's hard to determine if that's really a secant line. But now our slope is up there at 112. You go, well, is that really a secant line? Well, if I zoom in close enough, it still is a secant line, right? I mean, I still got a secant line. It's just a slope between 2 points. As I slide it closer and closer and closer, now I'm up to 120. I can move this graph. Well, what happens is, notice what happens when I drag this point all the way down to here. Notice it's undefined. Well, that's because my 2 points are the same. And I can't have that, because if my 2 points are the same, then suddenly I can't find the slope between the exact same point. I need 2 distinct points. Well, so let me just pull it off a little bit away from there. Notice what happens when I just pull it a little bit away from there. I could then zoom in. Notice it's 127.68. If I zoom even closer in here, if I drag it even closer, notice now it's 127.84. I think I maybe can get it a little closer. Well, I would have to zoom in a little closer to get it closer, but let me just stop there. It would almost suggest that this value of the slope of the secant line is 128. But let me do something, and let me zoom out, and let's take a look at what this graph now looks like when we look at where we started. I want you to take a look. I have 2 distinct points. They're really close to each other, right? I mean, it's 2 really distinct points. One is the point 1.01, and the other one is 1. But notice what that graph looks like. That really looks like more of a tangent line than a secant line. And if I move that point closer, it would, and that's where we could use the idea behind limits to move it closer. If I go back to this, you can pause. I'll go back here. You can pause this. You can play around with this if you wanted to. If you wanted to click that link in there, you'd be able to play around with it. But you can stop the video and pause and find that if you want. Let me go back to this. So this idea of the instantaneous rate of change. The idea of this instantaneous rate of change is we're looking at the slope of a line, and really this line that we're looking at is not just a line, it's a tangent line, right? It's a tangent line when x equals 1. Now, in order to squeeze these 2 points together, I'm going to have to use this idea that we talked about in the first unit, this idea of a limit. And so what I want to think about is you got the slope, and really the slope of between 2 points is y2 minus y1 over x2 minus x1. And so we got this slope. Well, notice that if I want to write the slope between points here, we wrote the slope between the 2 points when we were doing the average rate of change. We just did the slope between the 2 distinct points we have. Now we're going to think about this in a little more theoretical way, where what I'm going to do is I'm going to say that we have one point for sure, that is the point 1, 144. Okay, that's the first point. That's point 1. Now, if I wanted to, I'd love to get a point in here, and I'd really love to get it even closer. But I need to kind of think about what that point might be. That point is 1 plus some value, and f of 1 plus that same value. Okay, so if I wanted to draw the line or write the line between those 2 points, wouldn't I do f of 1 plus h minus f of 1, which is 144, divided by 1 plus h minus 1. And ideally, I'd really want to take this, and in order to squeeze that, what I really want to do is make h get closer and closer to 0. If I did this using limits, I could make that h get closer and closer to 0. I could essentially squeeze those points together, much in the same way I did that here. If I go back to this, and if I think about this idea of h, right now, h is 4 on this because I'm going from the point 1 to the point 5. But as I notice as I squeeze these points together, as I move this point, notice my h value is getting smaller and smaller and smaller. So here's my h value at 2.9, and my slope is changing. And notice what I have here is this is the slope. But I didn't write the limit notation, but I'm doing the limit notation when I take this h and I make it closer and closer and closer and closer and closer and closer. That idea is the idea behind this idea of the instantaneous rate of change rather than the average rate of change. And I'm using this idea behind slope. I'm just doing the same slope that you've done for years and years and years. So let's summarize some of this. The average rate of change of the function over an interval from a to b, call this b, is f of b minus f of a divided by b minus a. That's really just the idea of slope. That's where, if I have this is f of b, this is f of a. The instantaneous rate of change of a function at f of x equaling a. Now what we're doing is we're doing something a little bit different, because now what we're trying to do is we're trying to squeeze these points together. We're trying to move that point together. Well, instead of talking about this being b, so I'll leave it as there as b on there, but I'll change colors a little bit, is we're going to call this a plus h, which would mean this is f of a plus h. But in our case now, we're going to try to move this point closer and closer that way. So we're going to use the limit as h goes towards 0. And so as we move that point closer and closer and closer to this point a, we're going to do f of a plus h minus f of a divided by a plus h minus a. Well, notice that denominator, I'm just going to simplify that denominator into just being h. That idea right there is the slope of the tangent line when x equals a. The one above it was the slope of the secant line. So the average rate of change is the slope of a secant line. The instantaneous rate of change is the slope of the tangent line. So keep that in mind. And what you have is you have this here. Remember that in here, One is a difference quotient. Both of them are difference quotients. And that idea behind a difference quotient is a super important thing in calculus, because in the AP exam, oftentimes when they're asked something like this, the average rate of change, they really need to see a difference and a quotient. So, there I just wrote the same thing down twice, maybe a little bit cleaner the second time. So the rate of change, and really what I'm talking about over here is the average rate of change, is the slope of a secant line. The instantaneous rate of change is the slope of a tangent line. This is our first idea of that we're going to keep on building on of what a derivative is. And we'll talk more about that tomorrow. But the idea right now is we're just trying to get back here and squeeze these points together. Hopefully that makes some sense. The Delta Math assignment will continue to expand on this. That's it. Thank you.